In today's lecture, we'll be talking about sensors for flow. So we will see how we can actually measure the flow of a liquid or some gas. And we will also learn how to install those sensors correctly in an application. So first of all, let's take a look on how we can actually measure the flow, because there will be two ways how flow can be measured and evaluated. The first possibility will be the volume flow, which is some amount of your substance that passes through a certain point or cross-section in your unit of time. So typically we will be using the symbol Q, V, and the units of volume flow will, for example, be cube meters per second, or it could be cube meters per hour, for example. Anyway, it's some unit of volume per unit of time. The second possibility how we can measure flow is to measure mass flow. And mass flow obviously is some given mass that passes in a unit of time. So we will denote that as Qm, as mass flow, and the units will typically be, for example, kilograms per second. You will see that mostly the principles that we will see today will measure in some way volume flow. And the last one, the Coriolis flow, will measure directly the mass flow. So it depends on the principle of the flow meter, what do you actually get. Of course, it is possible to recalculate between volume flow and mass flow if you know the density. So you just need to measure the temperature of your substance and then to find in a table the density, and it's possible to recalculate between those two. So let's take a look on how we can actually do that. It's quite easy. If we have volume flow, we can say, okay, it's some cross-section times the speed, and this is the third way how we can actually measure flow. We measure the speed of our substance, and we multiply it by cross-section. So those two ways, volume flow and mass flow, those are the definition principles of flow. But we will see that some of the flow meters will also measure the velocity and in a pipe, for example, and then by multiplying this velocity by the cross-section we can get flow as well. However, this is not the direct definition of flow. So if the flow meter will use this principle, it will not be possible to use it for calibration of other instruments. But you will see that this is a quite common principle. For example, if you want to measure a flow in a pipe for a heating system, let's say, then those flow meters are based on measuring speed. And the second formula shows you how you can actually recalculate between volume flow and mass flow. You can see that here we have just the density, and this is the single variable that we need for recalculating between mass flow and volume flow. So let's take a look on what principles can we actually use to measure flow in industrial systems. Now the list that you see here is definitely not a complete list of principles that you can find in flow meters. This is only a selection. And out of this list we will be discussing again only a subsection. Those are the flow meters that are shown in green. So we will be discussing 4 principles how we can actually measure pressure. The first one will be differential pressure, which will be very closely related to last week's topic where we discussed pressure gauges, because here we will use the pressure gauge to get the flow rate, and for this we will use an orifice plate. The second possibility will be ultrasound, so we will use ultrasound to measure somehow the flow rate in a pipe. Then we will discuss the electromagnetic flow meter, and at the very end we will be discussing the Coriolis flow meter. So here are the 4 flow meters that we will be discussing today. The other flow meters are also used in industrial sensors. They are a little bit less common, and since we have only one lecture devoted for flow meters, it would definitely not fit into this one lecture. So that's the reason why we will be discussing only those 4 selected principles. So let's take a look first on the differential pressure gauges. We have discussed the pressure sensors last week, and there is a reason why we discussed first pressure and then flow, and the reason you can see here on this slide. The reason is that you can use a differential pressure gauge to measure the flow rate in a pipe. You can use an artificial restriction in a pipe, which is here shown as an example of an orifice plate. An orifice plate looks like this. It is a disc that has an opening in the middle. So it is like a barrier that is preventing the flow in a pipe, and you will see a pressure difference on the orifice plate. What we measure is the pressure in front of the pipe, in front of the orifice plate. We'll call that P1, and we measure the pressure after the orifice plate, and we will call that P2. Now, if we look on the static pressure in the pipe, we would see this pressure profile. So what is happening is that if we would measure the pressure here, we would see this pressure. If we see the pressure here, we will see this pressure there. If we measure the pressure here, we will see this pressure. So this chart that you can see here on the bottom is showing you the pressure distribution along the pipe length. And it is clear that we will see some pressure difference between the pressure in front of the orifice plate and after the orifice plate. Why is this so? This comes from the Bernoulli equation. You can see that here I have some speed of my liquid in the pipe. I will call that V1, and this liquid flows in some diameter d. And if I have to maintain the mass in the liquid, then the same amount needs to flow also through this smaller opening, and therefore it needs to be flowing faster. So the speed V2 that we have in this small diameter d the speed will be larger, and therefore there will be a pressure drop on P2. So in other words, the larger pressure will be in front of the orifice plate, and the smaller pressure will be after the orifice plate. And this is what we are looking for. We are looking for the pressure difference delta P, and from this delta P we can actually calculate using Bernoulli equation and other equations of fluid mechanics what will be the flow rate. So we use a pressure gauge that measures P1 and P2, and from this pressure difference we will be able to calculate the flow rate. Now in this link you can take a look on it on your own. There is a very good video showing this principle, and they have also some very nice animation about how this is actually used in industrial systems. So I highly recommend you to take a look on the video links that are in this presentation. Now the presentation is available in PowerPoint in Moodle, so you can download it, you can get the links, and you can take a look on them. Before we go to the calculation of delta P and the flow rate, now here we note that there is some permanent pressure loss. We can imagine this pressure loss as the loss of energy, because here we will be creating some turbulence, and this energy will be wasted as heat. The permanent pressure loss is not very large for an orifice plate, but it is still there. And we will see that this will be one of the disadvantages of the orifice plate when we compare this, for example, to the Coriolis flow meter or other flow meter types. Now let's take a look on how we can actually calculate the flow rate. So here on the top we have again our picture. We have the velocities v1 and v2, and we have the diameters, and we measure the pressure P1 and P2. So what do we know about this arrangement? We know that our flow rate Q has to be given by the cross-section of the larger pipe, so here this cross-section, times V1, because this is basically the flow rate. It's some area times the velocity. And we know that the mass will not disappear or will not be created anywhere in this place. So we can say that the flow rate in this larger cross-section has to be the same like the flow rate in this smaller cross-section. So this is saying in the first equation. So we see that the flow rate here is equal, so let's call it Q1, and this is equal to Q2, that's the flow rate in the orifice plate. The cross-section, that's clear how you calculate that, that's a simple geometry. Now we can use the equation that we can see here. We can actually square this equation, because later we will need this in the Bernoulli equation. So we can express the velocity here v1 as v1 squared, and that's equal to this part, and we'll later need this in the Bernoulli equation. And now from the Bernoulli equation we can find a relation between the pressure difference and between the velocities. So we can say that the pressure difference equals to this part of the formula here. Here we can say that this is the difference between the squared values of our velocities. Rho is the density. And at the end we can find what is our flow rate. So our flow rate is equal to this quite complicated equation. But we can see that it depends on the pressure difference, delta P under the square root. It depends on the density of our liquid. And then this first term is telling us that it depends also on the geometry. So it depends, we can see it depends on the cross-section A2 and on the ratio between A2 and A1. So at the end we can hide all this geometry and the properties of the liquid into two coefficients. One coefficient alpha and one coefficient that we will call epsilon. Now the coefficient alpha will hide the geometrical properties, and the coefficient epsilon will hide the properties of the liquid. except the density, because this also depends on whether you have a gas or if you have a liquid. In other words, if your liquid can be compressed or not. And that's the role of the coefficient epsilon that we have here. And the rest is telling us what is the geometry. So here we have the D, that's the diameter of my opening in the orifice plate. And here we see the pressure difference. So in an industrial application, you measure the delta P. Eventually, you measure the temperature so that you get the density. And all this is calculated and it gives you the flow rate. So if it's a flow meter based on this artificial restriction, it is nothing else than a pressure difference sensor plus some unit that will do the computation. So you can use directly a differential pressure sensor and then calculate it in the control system, or you can use a flow meter which has this calculation embedded inside. This is a picture how an orifice plate looks like. So it's a detail of an orifice plate, and it's a partially cross-sectional view. So we can see here that this is the orifice plate. So it's nothing else than a sheet of metal, for example, that is preventing the flow rate. Here we have the opening in the middle with some specified geometry and specified diameter. We'll see that in a minute. And here we can see that here this is the hole where we tap the pressure, and here we have the upstream, so the flow rate is going like this, and downstream is behind the orifice plate. So here we'll have a larger pressure. In my calculation this was P1 and this was P2. The distance between the orifice plate and the holes for the pressure probing is given by some standards. So it is not an arbitrary distance or arbitrary diameter. It is defined by some standards that tell you what should be the diameter, how far should it be, what should be the roughness of your material, what should be the beveling of your edges here, and so on. So it's not as simple as making a normal hole and then tapping it anywhere. It needs to be very accurately manufactured. You can see that we have now an artificial restriction in the flow rate. The orifice plate would be a suitable sensor only for clean mediums. So only if you have a liquid, for example, or a gas that has no solid particles or abrasive particles, because the abrasive particles can destroy the geometry that we have here on the orifice plate. And we'll see the advantages and disadvantages in a few minutes. Also note that the flow rate needs to go in the specific direction. We cannot measure with an orifice plate with a good accuracy in the other direction. That's again because of the geometry, because from one side on the orifice plate there needs to be a beveled edge, but not from the other side. So the orifice plate measures correctly in one direction only. And as we will see later, there are also some other reasons why it is possible to measure only in one direction. Now eventually sometimes there might be some impurities in any liquids, so here we may have a very small optional drain hole that allows us to drain all the application and eventually remove some impurities from time to time. But in general, the orifice plate is good only for clean, non-abrasive media. Here you see few examples of an orifice plate. So the orifice plate is shown here. It's just a sheet of metal, and here we have the specific geometry, specific angles and edge bevels that fulfill the standards. Here you can see the orifice plate installed in an armature. So here is the orifice plate, that's this one, and here those screws allow us to disassemble all this assembly and to remove the orifice plate and eventually replace it. And here you can see some installation examples. So from the outside it's like a pipe, and here on the bottom you can see the orifice plate here, and this is the differential pressure gauge that we've been talking about last week. So we can see that here we have two valves so that we can close it entirely, and we can eventually remove this pressure gauge. So this is the pressure gauge. In most cases it is based on capacitive sensing, and it measures the pressure difference on the orifice plate. And you can note here this symbol. This symbol is telling me that the flow direction needs to be in this direction. So I need to make sure that in my application the flow is going only in the specified direction. The orifice plate cannot measure in both directions. And you can also note the distance between the orifice plate and between the armature here. And we'll see on next slide why this is so. So note here that there is a quite large distance between wherever you connect the orifice plate and between the orifice plate itself. And then there is some small distance after the orifice plate. And again, there will be a specific reason for this distance. So an orifice plate requires typically a very large installation space. So you cannot just install the orifice plate anywhere you like, but you need to keep this very large distance in front and this somewhat smaller but still quite large distance after the orifice plate. Let's take a look on some installation examples. On this picture you can see the correct installation if you are using an orifice plate, and if you need or if you are interested into correctly measuring the flow rate with an orifice plate. So always in the picture here in the middle there is the orifice plate shown in blue, and then we have some distance between the orifice plate and between something in front of the orifice plate, and then we have some distance after the orifice plate and again something. And you can see several pictures here, and those pictures show typical examples of what you may see in an industrial application. For example, here you may have some valve, and now note that this first example is full open, full way valve. So it is a valve that is either fully closed or fully open. So it's not a valve that regulates the flow rate. We can take a look here on the value, they call it A. And for this it's the table that's above the pictures. We can say A, okay. So we are in the second column, but now we need also to know something about the geometry of our orifice plate. And the geometry here is depicted by the coefficient they call beta. And it is the ratio between the orifice diameter and the pipe diameter. So as we see, the correct installation is not only a question of the distances and whatever we have in front of the orifice plate, but it is also a question of the geometry of the orifice plate itself. So let's take a typical example where the ratio would be, for example, 0.63. So 0.63 means that I have some diameter of my pipe, and the diameter of the orifice plate is this diameter times 0.63. So it's smaller than the pipe diameter, of course. And we can say, okay, now we have this geometry and this case, and we see that we need to maintain at least 16 pipe diameters. So we have the orifice plate here, the pipe has some diameter, and we need to maintain a straight section without anything that is longer than at least 16 times the pipe diameter. So that might not seem that much, but if, for example, you would have the pipe diameter, let's say, of 10 centimeters, then this would need to be 1.6 meters. So it might be quite a problem to find a straight section that is not interrupted, and that in the upstream and downstream directions has the correct distance. For all the other cases, we can see that it gets even worse. The case where we have the fully open full valve is the easiest to solve. For example, let's take a look on case F. Here, okay, F. And case F is where we have right angle bending. So we have our orifice plate like that, and here we have one bending in front of the orifice plate, and we have one bending after the orifice plate. And in this case, we need to maintain at least 22 lengths times the pipe diameter. Let's take a look on case C here. Case C is where we have 3 right angle bendings. That looks quite extreme, but there is a bending that goes like that, then a bending that goes straight into the plane, and then a bending that goes in the right direction. So in this case, you can see 52. Now the reason why we need to maintain all this very long distance is that we need that the flow is steady. In the ideal case, we would like to have laminar flow in the pipe. So in order to make this flow steady, we need to have this very large distance. And you can say, okay, 52 pipe diameters, that might be something impossible to achieve. So in this table, you can always take a look and select the correct installation. In general, the installation of an orifice plate requires a quite large distance in front of the orifice plate, and after the orifice plate you need in general about 5 pipe diameters. Of course, if you have a longer distance it's better, but it is being said that 5 pipe diameters is the minimal distance after the orifice plate. And we will see that similar conditions will apply to almost all flow meters. So almost all flow meters will require some distance upstream and some distance downstream, with the exception of the Coriolis flow meter, which will not require that. And that's also one of the reasons why the Coriolis flow meter is very popular in industrial applications. Here you can see an example how an orifice plate is installed. We can see the orifice plate here. It's installed in an armature so that you can remove the orifice plate, and you can exchange it. You can verify if it's still working fine. We can see here that we have some walls that allow us to disconnect all the measurement system from our main pipe. So if we close this valve, we can remove the pressure gauge, we can remove the temperature probe, and so on. And you can see that these impulse lines, they are going to the differential pressure gauge. They may eventually go to a pressure sensor if we want to compensate, for example, for atmospheric pressure changes. And here we have also a temperature sensor. And those three numbers, they go to what's called a flow computer, and this flow computer takes in the pressure difference, takes in the temperature. From temperature it will calculate the density, and from differential pressure it will calculate the flow rate based on the equation that we have seen. And eventually it will take the barometric pressure into account as well. So it might be even a more complicated equation if we use the data from this pressure sensor. And at the end, from this flow computer, we'll get a reading either on a display, or we'll see that on some computer screen, and it will be connected to a control system of our plant, for example. So let's summarize the advantages and disadvantages of an orifice plate. So what are the advantages? The orifice plate can be used for all mediums. So it can be used for liquids, for gases, and steam. So all three. This will not be the case, for example, of the ultrasound. We'll see that it will be different. An orifice plate is a very simple device. It's basically just an artificial restriction in the pipe. So it can measure up to very high pressures and up to very high temperatures. So those data are actually coming from some data sheets of manufacturers. So they say that it can measure up to 42 megapascals and up to 1000 centigrade. So out of those four principles that we will be discussing today, this is the highest pressure and highest temperature range. Except when you need to change the orifice plate itself, you don't need to interrupt the process if you want to exchange, for example, the differential pressure gauge. As we have seen here, we have some valves that can be closed. So if I want to exchange or calibrate my differential pressure gauge, I don't need to interrupt the process which is running in the main pipe. Of course, if I need to exchange the orifice plate itself, I need to close this pipe, I need to change the orifice plate. So then it requires to interrupt the process itself. It is working in a wide diameter range. So an orifice plate may work typically between 10 millimeters and about 5 meters. The orifice plate is not a single device that you may use as an artificial restriction. You can use a venturi tube, a venturi nozzle, for example, and all this is based on the restriction type. So in general, the restriction type devices can be used in those pipe diameters. So you see that it works from a very small range of diameters up to about 5 meters. If we count the pitot tube also in this group of devices, the manufacturers say that this is working up to 12 meters. So if you have an open channel, if you have some very wide diameter of your pipe, then you don't need to use an orifice plate. You may use, for example, a pitot tube. Now, what are the disadvantages of an orifice plate? The orifice plate has a limited turn down ratio to a value of 4 to 1 and eventually 5 to 1. Now what does this mean? The turn-down ratio is the ratio between the maximal and the minimal flow rate. So it is telling me if I have some specified minimum range, then what will be approximately my maximum range that I can measure. In other words, it means that I cannot measure from zero flow to some very large flow rates. If you remember the equation, then we had a square root of delta P, and if I have a square root of a small number, it will be even a more small number. So that's the disadvantage of the orifice plate. It cannot measure accurately small flow and large flow as well. So for example, if I would like to measure, let's say, air when I have, for example, 1000 cubic meters per hour with an orifice plate, then I could do that. But considering this ratio, it's telling me that the minimal flow rate that this device will be able to measure will be approximately 200 cubic meters per hour. So the ratio between max flow and minimum flow is about 5 to 1. The disadvantage is also that we can eventually damage the orifice plate, particularly if we have a dirty fluid that is flowing in our orifice plate. So if it would be, for example, a mixture of water and sand, then the orifice plate is actually not a good idea, because very soon you would destroy the edges on the orifice, and it would not measure accurately. So the orifice plate is suitable only for clean fluids. And I was already talking about this last disadvantage. The orifice plate requires a very, very large distance both upstream and downstream, and we have seen that in a table. It can be very large distance. So it might be even impossible to install the orifice plate in an application, because you simply will not have enough space and enough straight sections in the piping so that you can install the orifice plate correctly. So this is, in my opinion, the biggest disadvantage of the orifice plate. Some more disadvantages, but this will mostly apply to all flow meters except the Coriolis at the end. So it will not be able to measure small flow, because we've seen that we measure pressure difference, and for small flow we'll have a very small pressure difference. It is not suitable for very viscous liquids. Again, for the same reason, you will probably block the pressure, the impulse tubes to the flow meter as well. It does not measure directly density, concentration, and viscosity. That will be again mostly the case for all pressure gauges except the Coriolis. But you can calculate density. You will measure the temperature, and you can calculate density. And as I was already saying, it is not suitable for abrasive liquids. So if you have a mixture, for example, in mining applications of water and something, then the orifice plate is definitely not a good idea. Let's take a look on the second flow meter, and this will be the ultrasonic flow meter. So now it will use a quite different principle, but at the end it will measure in a very similar fashion. The ultrasonic flow meter is also a meter that is based on measuring velocity. So we measure the velocity of our fluid in a pipe, and then we multiply that by the cross section that is known and constant. So in order to do this, we need two transducers. One transducer is here, the second transducer is there. Now imagine that we will send an ultrasonic signal, for example from the transducer on the left. So the transducer will send the signal, it's going through the wall, through our liquid, it hits the wall on the second side, it's being reflected, and then it's traveling again through the liquid to the receiver. So at this time, this number 1 will be a transmitter and this number 2 will be a receiver. It is clear that the time difference between the transmitted pulse and the received pulse will be some function of the velocity. Now we use this number 2, this transducer, as a transmitter. So we transmit a signal like that, we get the reflection like this on number 1. Now if the flow rate would be 0, it means that the time it took from 1 to 2 and the time it took from 2 to 1, so this time and that time, they would be equal. So for 0 flow rate, we would get 2 equal times. If, however, the fluid is flowing in one direction, then if I go from 1 to 2, it will take me a shorter time than if it's traveling against the stream. So if I take the time from 2 to 1. So if my flow rate is going from the left to the right, time from 1 to 2 will be shorter than time to 2 to 1. And we can of course calculate a function, and we can relate this to the flow rate. So the ultrasonic flow meter is equipped with at least 2 transducers. We transmit a signal from both, and we are looking for the time difference. So if you would plot that on an oscilloscope, for example, you would see something like this. This is when I transmit from 1 to 2. So I start some ultrasonic pulse, I wait for the reflection, and I get the time number 1. And this is from 2 to 1. I start the ultrasonic pulse, I wait some time, and now as I'm going against the flow direction, it takes longer before I get the reception, and I get time 2. So from the difference between T1 and T2, it is possible to calculate the flow rate. Now we don't need the equation because we actually do not care right now, but there is a function that relates the time difference versus the flow rate. Again, there is a quite interesting video, so I recommend you to take a look on this link. It explains quite nicely how this works with some animation, and they also show us some examples of installation of those transducers. The transducers, they do not have to be arranged like this, but in larger pipes it's typically done in such a way that one is on one side of the pipe and the other one is on the second side of the pipe, and then they send the signals like that. But it can be installed like this on a single side. That's typical for smaller pipe diameters. Here is how such arrangement looks like. So on the left here we can see the piezoelectric transducer. So it's a piezo crystal that is being excited with a voltage. Now you can imagine it like we have a crystal, for example, in a cigarette lighter. You press this crystal and this gives you voltage. Or if you reverse this, you have to apply voltage, and this will change the shape, and it's producing mechanical vibrations in the ultrasonic range. So the voltage here that we apply is somewhere from tens of volts up to hundreds of volts, and this will produce us some ultrasonic signal. It's typically in the range of a few megahertz frequencies. Now this ultrasonic signal travels through this sensor, travels through the pipe wall and through the fluid. Then it gets reflected from the pipe wall and travels back to a receiver, and we can simply calculate what is my flow rate, which we can see that it's proportional to the time difference. And then if we know the cross-section of my pipe, we multiply the speed by cross-section, and we get the flow rate. So this is again based on measuring speed of my fluid. Of course, it will be temperature dependent, because the speed of sound will depend on temperature. So at some point we will need to measure the temperature of the liquid as well. What are the conditions where we can actually use this ultrasonic flow meter? Now we need that the ultrasonic signal travels correctly in the fluid. So we need to watch for eventual bubbles of gases in our liquid. So for example, you can see here we have some bubbles on top of our pipe, and that might be a problem. The same problem might be on the bottom. If we have some impurities that may sediment on the pipe, the ultrasonic signal might be blocked also by those sediments. So never install the ultrasonic flow meter from top or from the bottom of the pipe. The correct installation is like that from the sides, so that the ultrasonic signal can travel back and forth and will not be prevented by eventual bubbles or eventual sediments. There is also a limitation by volume of how many gases and solids we may have in the liquid. So it is said that approximately at maximum 2% by volume of gases is allowed in the liquid, because if we have a gas, we will have a different sound velocity in the gas than in the liquid itself. And also, if we have solids, they may disperse the signals, they may attenuate it, and it might be a problem for the reception. So those are the limitations. Again, you see that it's suitable mostly for clean medias. Another limitation is that at all times the pipe needs to be full of my liquid. So the ultrasonic flow meter will not work correctly if you have a partially full pipe, which you can see here. The reason is simple. Even if I would measure correctly the speed profile here, I do not know what is the cross section, so I would need to calculate this, but instead I know what is the total cross section in here. So if your pipe is not fully filled, then your ultrasonic meter will not measure correctly at all. You can see here a more detailed explanation why do we have to avoid the solids in the fluid, in the liquid. You can see that, okay, here those are my particles that I have in my eventual fluid. I send the ultrasonic signal, but the ultrasonic signal will be attenuated on those particles. They will reflect the sound, and we will not be able to receive the echo by the receiver, which will be we are expecting that the sound is traveling like that, and we are looking for the reflection on the receiver that will be somewhere here, and we simply may not be able to receive enough of this signal so that we can correctly time it. So the ultrasonic flow meter is suitable only for clean fluids. Here you have an example how such device may look like, and again a quite interesting video how this is useful in the chemical industry. Now the advantage of the ultrasonic flow meter is that we measure through the pipe wall. So our sensor is not in a direct contact with our liquid. So the liquid might be an aggressive liquid, it might be an acid, for example. It might be corrosive in some way, but it's in a pipe and we measure through the pipe wall. You can see that this is a clamp-on system. So the sensor, which is this thing and this thing, this is installed from the outside, and we don't have anything that is in direct contact with the liquid itself. So it's fairly simple to install the flow meter. We can even retrofit our application if for some reason we find out that we need to measure flow in this pipe. We do not need to interrupt the process. We do not need to interrupt the pipe. We just clamp the sensors outside like that with a clamp-on system, and we can measure the flow rate. So it's quite useful, for example, in the chemical industry. It's very safe. We are not in direct contact with the flow meter and with the liquid. So what you can expect. The ultrasonic flow meter can measure liquids and gases, but only if they are sufficiently clean. We have seen about 2% of gases in the liquid and about 5% at maximum of solids. We can expect to have a field accuracy of about 2% when the system is installed correctly. Now this applies to the clamp-on system, and under reference conditions, that means in a lab, for example, or if we really calibrate properly all the devices, we can expect an accuracy of up to 0.5%. So compared to the other flow meters, such as especially the Coriolis, this will have somehow lower accuracy. Lower, it means by instead of let's say 0.5%, you might have something like 2. But it is suitable for chemical industry, where you have some corrosive liquids, for example, and you don't need to interrupt the pipe. Now the manufacturers, they give us the diameters of the pipes. So typically the clamp-on system might be used to diameters up to around 5 meters, and the inline system up to about 2 meters. Now the inline system is where you have the ultrasonic flow meter as a device that is installed with an armature directly in the pipe. So for the inline system, you need to interrupt the process, you need to drain the pipe, and then you can install the flow meter. But for larger diameters, it's more advantageous to have the clamp-on system, at least from installation point of view. You can see the process temperature. It is definitely lower temperature range than the Orifice plate. For the Orifice plate, we had something like maximum 1000 centigrades. Here we have roughly 170 centigrades. but we're not in direct contact with the liquid itself. What are the advantages? If we are talking about liquids, the turn-down ratio of an ultrasonic flow meter is about 50:1. Remember, for the Orifice plate we had about 5:1. So we can measure in a much larger ranges of pressures and flow rates. So again, it cannot measure from zero flow and then we have some maximum flow, but this ratio is already quite large, so we can see 50:1. For the clamp-on design, we do not have any pressure loss, so we have just the pressure loss in the pipe, which is very small compared to anything else. So out of all those flow meters that we will discuss today, in terms of pressure loss, the ultrasonic is the best because it's clamped on the pipe and has no pressure loss. The same, there is no damage due to abrasion or corrosion from the fluid, simply because the sensor is not in contact with the fluid. It allows us to measure in both directions. So for the Orifice plate, we were able to measure only in a single direction. With the ultrasound, we can measure in both. We can measure from the outside of the pipe without interrupting the process. And since it's clamped from the outside of the pipe, the price is virtually independent on the pipe diameter. So you have a clamp-on design that will fit on a pipe with 10 centimeters and even on 1 meter, and it will be basically for about the same price. Of course, it will have some disadvantages. It is not suitable for small flow rates. It's not suitable for very viscous liquids. We can see that it does not measure steam. We cannot use it if we have some mixture of liquid and a solid. We cannot use it if we have some mixture of gas and liquid. And for the clamp-on system, we have no traceable calibration. That's because for the clamp-on system, the accuracy will depend also on how it is mounted. So we cannot relate the calibration of this device to some calibrated flow meter, for example. Here are a few examples how those devices look like and examples where they can be used. On this picture you can see the clamp-on system. So this is the clamp-on system. You can see that we have two sets of transducers. So one is clamped on to the pipe, the second one at a certain distance that varies based on the pipe diameter, and it's just clamped on the system from the outside. I have a picture on the next slide, I believe. And you can see the areas where this is typically used, so chemical industry, pharmaceutical, oil and gas, water supply, and so on. One of the videos that I have linked in the presentation is also giving you a few examples. I believe it's from the water supply industry. Here we can see an example installation. So you can see a pipe like that, those two transducers clamped from the outside on the pipe, and this flow computer measures the flow rate. So that's the clamp-on system, and here you can see the example of the inline system. So it's a pipe that you use two armatures to mount into the piping system. And here you see two transducers, and from the second side there will be two more transducers, and it's then connected to this electronic unit that takes in the signals from the transducers and calculates the correct flow rate. How to correctly install it? Well, we will again need some distance upstream and some distance downstream. Compared to the orifice plate, however, these distances, especially in the upstream direction, will be much smaller. So let's say we have a bending of 90 degrees, and in this case we need to keep at least 5 pipe diameters in front of the flow meter. After the flow meter, it's again 5 pipe diameters, so that's the same as for the orifice plate, but in front we can see it now, it's only 5. For the orifice plate we had something like 20 or 30 or 60, dependent on what was in front of them. If, for example, you have a pipe pump, then we need a longer section to allow the flow to stabilize itself, and here we have 15 pipe diameters. If we have something like a valve or fully opened valve, that might be about 10 or 5 times. Now this is a valve that is controlled, and for this we need even longer distance, so about 40 in front of the flow meter and about 10 after the flow meter itself. But it's still shorter, so it may fit in your application if the orifice plate is not suitable. The third type that we will be discussing is the electromagnetic flow meter. Now this electromagnetic flow meter will need a specific liquid. We will need that this liquid is electrically conductive. So it will not work for a liquid that is not conductive. So we cannot use it, for example, for oil that is not conductive. But we may use it for water, because water is slightly electrically conductive. So how does it work? It is using electromagnetic induction. You can see here that we have a coil. Now this coil is creating us a magnetic field. So we create a magnetic flux in this direction with this orientation. This liquid is conductive and this liquid flows. So now we have, let's say we will plot this liquid as some particles, and some of them will have positive charge, some of them will have negative charge. And now we have this charge, that's moving like that, and we have a magnetic field. From physics, we know that when we have a charge that's moving and we place this charge in a magnetic field, there will be a force that will be acting on this charge. So what will happen is that we will have positive charge on one side of our pipe and negative charge accumulating on the other side of our pipe. You can see here the rule, and that is telling us what is the direction of the current. This is the right hand rule. So the thumb is pointing in the direction of the movement. This index finger is showing us the direction of the magnetic flux, and the other fingers are showing us the direction of the electric field that we are creating. So here we have two electrodes that are used to sense the polarity and amplitude of the electric field that we have created in this way. So at the end, we can say that the voltage that we measure is proportional to the speed of the fluid in our pipe. So at the end, this type of flow meter also measures the velocity, and we multiply that by the known cross-section, and this gives us the flow rate. Again, there is a quite interesting video on this first link that I highly recommend you to take a look. There is an animation how this works, also with the particles, and also with some industrial applications. To give you an idea about the size of this voltage, here is an approximate value for water. Approximately for 1 meter per second of velocity that we have in a pipe, we will get about 300 microvolts. So the voltage is fairly small. It's definitely not like a generator that could power something, but we can use it to measure the flow rate in a pipe. Now we want to eliminate external magnetic fields, and that's the reason why here we are using a coil and not a permanent magnet. So this chart on the bottom is showing you how do we actually reorient the direction of the magnetic field. First, we measure in one direction. That's those are those rectangles on top. We measure we apply the magnetic field in one direction. We measure the electric output, and then we reverse the polarity of the magnetic field. So then we are here at this section, we measure it again, and the signal that we get from the flow here, the voltage, will in this case be a function of the flow rate, and then from this voltage and that voltage we can calculate the flow rate, and we can eliminate external magnetic fields. Because, for example, if we would have a magnetic field, a permanent magnetic field, that would be oriented in that direction, then by reversing the polarity, we are able to eliminate this permanent magnetic field. So, since we reverse the magnetic field, we are able to eliminate external disturbances. And that's also explained in this video. How does it look like if we make a cross-sectional view of this flow meter? It's an inline system, so here we have the armatures that allow us to connect the sensor to the piping system. You can see that here this is insulated, this blue stuff, that's an electrical insulator, because we need an insulated system. And here this is the coil, like that. So this coil will create the magnetic field that is going like that, in that direction. And in the perpendicular direction to my plane, to my picture, we have the electrode. So one is from one side and the other one is from the other side in the same orientation. So our liquid flows like this. It's in the magnetic field that is oriented like that, and in the perpendicular direction we will be able to measure the voltage. So if we take a look on the whole assembly, it looks like that. Here this is the pole shoe that is distributing the magnetic field in the pipe, so it's orienting the magnetic field like that uniformly in the whole cross section. And here you can see the assembly of the electrode, which is going in the pipe, and then there would be another electrode from the other side. The whole tube is insulated like that, so here they have some polyamide lining so that it's it is electrically non-conductive. And from the outside, we then, above all this, will have some magnetic shielding, so that the magnetic field from the outside will not penetrate that much into the flow meter itself. Here are a few examples. Again, it's used, for example, in the food industry, in water processing industry, or in chemical industry. It requires a conductive liquid. So if you are designing an application with those sensors, you first need to make a list of properties of your liquid, so that you're able to find if this principle is suitable or if it's not. In terms of temperature range, it is approximately the same like for the ultrasonic. You can see here it actually depends on the material of the liner that insulates that. So if it's PTFE, for example, which is Teflon, for this specific version they say up to 130 degrees. For this they say up to plus 90 degrees. So it's also related to the type of the flow meter. And you can see also the pipe diameters. They are again roughly the same like for the ultrasound, so from few millimeters up to few meters of the pipe diameter. What can we expect? Well, it's suitable only for conductive liquids. So it will not for gas, for example. It will not work for a liquid that is not conductive. The expected accuracy is about 0.5%. If you are looking for more accurate sensors, you may find something like 0.2. The pipe diameters, they go up to 2.5 meters roughly, and pressure is going up to about 4 megapascals. The temperature range is from approximately -50 to about 180. So it's roughly the same like for the ultrasound. Definitely a lot smaller temperature range compared to the Orifice plate. On the other hand, the electromagnetic flow meter has a very large turn down ratio, roughly about 1000 to 1. So it can measure accurately very small flows and very large flows as well. So electromagnetic flow meter has about 1000 to 1, the ultrasound had about 50 to 1, and the Orifice plate had about 5 to 1. So compared to the Orifice plate, we are at least a few orders of magnitude better in the turn down ratio. We have essentially no pressure loss. That's the same like the ultrasound. And since we measure the conductivity, and there is nothing that could be mechanically damaged in the flow meter, this electromagnetic flow meter is suitable also for highly abrasive liquids. So it can measure, for example, a mixture of water and sand, which you may find in the mining industry, or some ore slurries, so a mixture of an ore and water. The disadvantages: it does not work for non-conductive liquids because we rely on the electrical properties, so we cannot measure a liquid that is not conductive. We may get errors with sediments because we measure the flow rate as a speed of our liquid in a pipe. So if we have a sediment on the bottom, then we do not have the full cross section. It does not measure cryogenic liquids. Well, they're not conductive, so if they're not conductive, then we cannot measure them. It cannot measure steam or gases because they are not conductive. And the same disadvantage like for the ultrasound, it measures only for completely filled pipes. So if we have a pipe that is just partially filled, it will not measure properly. So how to install the flow meter? Well, the general condition is that the pipe must remain full at all times. So if we imagine this arrangement, here we have the electrodes from the sides. We have some reference electrodes, but now that does not play any major role. But we can see here that we cannot have only a pipe that's partially full. So it's not recommended for this reason to install the flow meter in the horizontal pipe that goes like that, or in a pipe that goes downwards. So because if you install the pipe like this, then you may have bubbles in here and your pipe is not full at all times. And the same also here in this arrangement. The flow is going like that, the bubbles will go up, and you will have not a full pipe in the flow meter. So the recommended installation looks like this. If you have a horizontal pipe and you need to measure the flow rate in there, you need to bend downwards the pipe like this. Then you install your flow meter and then you continue in the pipe. So this installation makes sure that even though this pipe is not full, this section will be full at all times because of gravity, and all the eventual sediments will accumulate here and all the bubbles will escape here upwards and will not be inside of your flow meter. So typically then it looks like that. Straight pipe was going like this. They needed to install the flow meter so that they made a bending like this. This is the flow meter, and this siphon type installation assures that you have a full pipe at all times. You again need to maintain some distance upstream and downstream. So here we see that at least 5 pipe diameters in front and at least 2 pipe diameters after the flow meter. So we are steadily decreasing the requirements for this distance. So ideal mounting for this type of flow meter is in a vertical pipe. So you have a vertical pipe like that, and it's working in the same way like we've seen on the last picture. So even though this will not be full, then this system has to be full at all times, and eventual sediments will stay here and eventual bubbles will be there. Okay, so the last flow meter will be a Coriolis flow meter. And we'll see that the Coriolis flow meter is very often used in many industrial systems because it will have many advantages. So how does it work? Let's imagine that we have a pipe like that. I will start on this picture on the right. So here is the input to my pipe, like this, and the fluid is flowing in this direction. Now this pipe is bent. You can see that it has a shape like this, and here we have the output of our pipe to the right. Now the liquid is flowing. It tries to flow in a straight direction, so it would like to flow straight like this in that direction due to the inertia. But my pipe is bended like that, so it has to flow along the pipe like that. Now what we do is that we also impose an oscillation of this pipe, and this is shown here with the omega. So we impose some angular velocity omega. You can see that here in this animation. Now, when there is no flow, the pipe is oscillating like this. So it's moving back and forth, and we see that there is no additional twisting that is created. However, as soon as we increase the flow rate to non-zero values, we will see the Coriolis force that will act on the liquid. And we can actually calculate the Coriolis force. You can see the equation here. Now I forgot here the sign. There should be a vector multiplication here. So it is v, which is my velocity of flow, times omega, which is the imposed angular frequency. So we can see from this equation that if flow is 0, then v is 0, and then the Coriolis force is 0. As soon as we have some non-zero flow, we will see some Coriolis force acting at this section of the pipe, and the same, but with different sign, will be acting at this section of the pipe. So we have one Coriolis force that goes down at the left section, and we have one Coriolis force that goes up in this section of my pipe. So this will create an additional twisting on this tube. And we can see the twisting here. We can see that the pipe moves up and down with the same frequency like before, but now our both ends are twisting differently. We can see that when this end is twisting up, and this end is twisting downwards. So what is happening in a Coriolis flow meter is that we measure the oscillation of this pipe and of those both ends, and we are looking on those position info. And there is a direct relation between the position and the Coriolis force that we have here, and from the Coriolis force we can calculate what was my flow rate. Again, there is a very nice video in here on those links, so I highly recommend you to take a look on that. So what we are actually measuring is we are looking for the displacement of my tube. So if we look from the upwards direction on the Coriolis flow meter, we see something like this. This is my pipe, it's going like that. And in the middle we have a driving coil or coils that impose this oscillation, that create this oscillation. Of course, on the animation, the movement is exaggerated. It's much smaller in reality. And on the sides of the pipe here we have displacement sensors. It might be, for example, an inductive sensor. And based on the phase difference between this pickup coil and this pickup coil, we can calculate what is the flow rate. And we can see here roughly again the same picture. It's moving up and down like that with some given angular velocity omega, and here I would pick up the motion with an with a position sensor. So what is unique on this Coriolis flow meter? We have seen on the equation that the flow meter, based on this principle, will be able to measure directly mass flow. So it's not related to velocity, it measures directly the flow of mass. This is a picture, again, what you may find inside. So here in the middle we have the oscillating system, so it's imposing the oscillation of the pipe back and forth, very slight oscillation. And here and here we have the sensors. Sorry, here I forgot to translate that. This should be the sensor, the position sensor for the pipe. So it might be typically an electromagnetic sensor or inductive sensor, something like that. And then we feed that to a converter electronic unit that takes this position sensor data and gets the correct mass flow. So if you open it up, it looks like this. You can see either one or two stainless tubes or titanium tubes. They are oscillating like that. And then we would have some position sensors, some driving coils, and also typically some temperature sensor that measures the temperature. So the advantage of if we have a two-pipe arrangement, then we are able to compensate some external movements such as vibrations, and therefore it will have no influence on the flow meter itself. And so here we can see how does it work. We have the pipe, it's moving back and forth, left and right, like that, and we are measuring the position. The flow meter, based on the Coriolis principle, does not have to measure only the mass flow, but it can directly measure also density. Because if you imagine, for example, water and honey, you impose some vibration, then this vibration will definitely be different, because we have different densities. And here you can see such an equation. So the resonance frequency of this oscillation is a function of the density, and this measurement is independent on the measurement of flow. So the Coriolis flow meter can measure directly the mass flow, and independently it can also measure the density of my liquid. So it can actually provide me more variables than just the flow rate. We can have a single or a dual tube. So in mechanical terms, the single tube version is simple, but it is sensitive to external disturbances such as vibrations. It has lower pressure loss than the dual version. On the other hand, the dual version is able to suppress external vibrations. So the selection depends on what environment do you use this flow meter in. Let's say the advantages and disadvantages. It measures directly the mass flow of liquids and gases. It measures directly the density, and for example, if we add something like PT1000, we can measure the temperature as well. It is very accurate. Typically 0.1% is quite achievable. It does not require any distance upstream and downstream, and it is able to measure or calculate the volume flow, concentration. It can measure viscosity as well. So out of those four principles, it is like the best principle, but it will be also one of the very expensive ones. It is able to measure low flow rates. It is able to work with cryogenic liquids. We don't have any limitation here. In terms of diameter, it typically goes up to about 500 millimeters. Pressures and temperatures are a little bit higher than the pressures for the ultrasonic and the electromagnetic flow meter. Again, this depends on the specific type of the flow meter. What are the disadvantages? Well, compared to the electromagnetic and ultrasonic, it has a higher pressure loss. It is not installed from the outside. And there is also a limitation that this type of flow meter can be used for single phase liquids, because two phase liquids will have an impact on accuracy. And it is also quite expensive compared to, for example, the Orifice plate, which is the least expensive one. Here are a few examples. You can immediately recognize a Coriolis flow meter because it has this specific shape. So in this shape, it's the tube that we have like this that's bent. And from the outside, you can directly tell, okay, this is definitely a Coriolis flow meter. You can see oil and gas industry and so on. So specific use. At the end, let me tell you how to install it correctly. Again, we need to watch for sediments and bubbles. But here the reason is that it may stay in the tube, and it may be quite hard or impossible to remove. So if you would have sediments, then this is a problem. They may accumulate in the bottom of your pipe. If you have air bubbles, they may accumulate on top of your pipe. So this is not a good way how the sensor should be installed if there is a risk of bubbles or sediments in your application. The correct installation of a Coriolis flow meter is again in the upstream direction like this, so that we have a full pipe and the sediments stay somewhere in the bottom and the bubbles stay somewhere in the top. So if I go back to my example here, we can directly say that in this application the flow was going like this, and they were pumping something from this bottom pipe to this top pipe. It was definitely not going like that. So that's it for flow meters, and on the next lecture we'll be discussing liquid level.